Yo, hello. Stream setup's weird. I don't know if I like that format or not. Yeah, it's actually better probably. All right, so I've got 7 minutes. I've got more time than I thought. Is my microphone on? That's the big question. It is, but it's quiet. All right, we don't really need desktop audio. So what are we doing today? That is a good question. And the idea is, as I was thinking, using Python, I'd try and construct a computer algorithm thing. So basically the way it works is, I remember how laggy everything is. Alright, let's draw some circles, because circles are cool. I would usually read chat if anyone's in chat, but it's like a 6-minute stream. This is probably not sensible, but yeah. So we got 6 circles. Let's label them, because why not? Ooh. D. Let's label this one alpha, just because I feel like it. And then we can connect these guys up. Oh boy. I should have drawn them closer together. Oh well. Alright, now that's assign weights, so we'll say 5. No, actually this isn't complicated enough. 2, 3, 5. It still doesn't feel complicated enough, but it's probably complicated enough to make it a thing. Alright, so you have different circles. The different circles represent like different places. So maybe we could think about these as different buildings, or maybe a university campus or something. And the numbers represent how long it would take you to get from one. So if we wanted to go, for example, from A to B, oh wow. Let's say a unit equals a minute. Wait, I should probably say that somewhere. Unit, minute, doing, 5 minutes left. So here, we've got a unit of 2 between A and B, so that means if we wanted to go from A to B, or a B to A, that would take us 2 minutes. And there's this particular problem called, I think it's called the minimum spanning tree problem, which basically states, okay, let's say also here, all the different locations aren't connected by roads, but we know we could build roads, and if we did, that's how long it would take. No, I've got a better idea. Oh boy, let's go to that. I'm changing this. Let's change color as well. Change everything. All right, we're saying units now. How much money? Yeah, say 500. Yeet. 4 minutes. So let's say we had these different locations and we had to connect them all up. And these are how much it would cost to build that road. So if we were to connect A and B, it would cost us 5 by 200, 1,000 quid. And we have to figure out what is the cheapest way of connecting everything. So one way we could connect everything is we could connect it like this, 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 this. I should grab a calculator. 1 sec. Alright, let's figure out how many units that is. The fact it's 500 quid isn't important now, we just need the lowest units. So that would be 5 plus 3 plus 11 plus 7, and that actually connects everything. That's 26. So this current way of doing it is 26. Yeah. But now we need to save that I've done it that way. Okay, I've got an idea. Let's copy paste it. Oh no. Let's go. Yes, there we go. The magic of computer science. Okay. So let's do that again. So what would we say? Like that. Is that the exact same? Oh, I've got it written on my calculator. Let's go. I think I've done it differently. I have done it differently. Okay, that's fine. Let's just recalculate that. 5 plus 2 plus 3 plus 11. So this way would cost us 21 units. But like, there's clearly other ways we could connect them. So one example is instead of K, an FN deal, we'll delete that. Okay. Let's just scribble it out. So let's say instead of going this way, we could go this way instead. And that would actually increase the cost by 1, because now we're going 3 instead of 2. But the point is that there's different ways you could do it. So obviously, with this example, we could just brute force all of them, but it turns out there's actually an algorithm called Prim's algorithm. Let's write his name up here. Actually, let's write Prim's because it says algorithm. And what it states is, oh gosh, I'm running out of time. What it states is that the algorithm works like this. You choose a node, so let's choose A, for example. And then what you do is from A, you choose the least expensive way you could go. So here it's 2. Now it connected at B as well. And then what you do is you keep doing that. You keep choosing the lowest one that's connected. So here, what's the lowest one? We could either choose 3, 5, or 5. 3 is the cheapest. Here we could go, we can't do 5 because that would cause, oh yeah, that's the other thing. You choose the cheapest that's connected, and that doesn't cause a cycle. This would cause a cycle. That's no good, because now we're spending money we don't have to. Because we don't need to go from here to here, because if we want to get from alpha to A, we just go B, A. So, yeah. So that, what's the cheapest now? You go 3 or 11. 3 is cheaper than 11. Now we could go either 5, 7, or 11. No. Yeah, and 5 is the cheapest. So now, because we used Prim's algorithm, we know this is the cheapest way to do it. So we've got 2, 3, 3, 5. Calculator. 2 plus 3, 3 plus 5, 13. So as we can see, we optimized it quite a bit. And how much money would that be? I mean, it doesn't really matter, but it would be 6.5 thousand. Oh. If you care about that. 13 by 500 gives 6.5 thousand. So that's Prim's algorithm, and that's how it works. But the reason why I'm here today is not because Prim's algorithm exists, as cool as that is, but because there's fancy things you can do with this. So right now, in order to find out the cheapest way is 13, to figure out this is the way to do it, that required me as a human, because I was looking at it and figuring out which are connected and which aren't. But it turns out you can do this algorithm in such a way that you could give it to a machine, if we like Python, or can we? So here, Python can do certain things. We can make more complicated things as well. Like if we wanted to say, it doesn't like that, of course it doesn't like that. So there we go. So we can make it do more complicated things like that. And you can instruct the computer to do different things through a programming language using Python, because Python is great and it works. But what it can do is it can only do deterministic things. So we need to turn Prim's algorithm here into something deterministic if we're going to make the computer do it. Turns out that's not too difficult. Well, that's the timer to say time's up, so I might need to go any second now. I can continue with this later. Alright, so how can we make this deterministic? Well, it just so happens that we can rewrite. Can I copy paste that into that? This works, I will be very happy. Oh my goodness, it works. Yes, okay. Oh, I wish I could shrink it, but my technology doesn't let me do that. So it just so happens we can write this out. It's a pretty crazy method. We write out our nodes. So we got A, those are our circle things. What's happening here? Oh, we got C and we got D. And we got alpha, which I cannot draw. And what you do is you write the same nodes. You can actually do any order, but it just makes it easier to read the diagram if you do it in the same order. This bit's not too exciting, but what you can do with this is pretty exciting. Alright, and then we can draw this to say, hey, this is a matrix. It's not particularly important, but it will be later. Kind of, actually, it's not important at all, but we can do this and it makes it feel cooler, I guess. So what you do is you read it like this. You say, what connects to A? Oh no, you ask, does A connect to A? And in here's case, the way it would connect to A is if we did that, but it doesn't. So we put a dash to mean no connection. We could put a 0. The only problem with putting 0 is, actually I'll show that in a second. Does A connect to B? It does. And what's the edge? It's a 2. Does A connect to C? It doesn't. Now you might be thinking, why don't we just put a 0? But the thing is, with a 0 is that could be an edge connecting A to C with a weight of 0, which it isn't. There's just nothing. So we don't put a 0, we just put a dash. You could put 0, but it might cause problems. Not that I can see, but maybe. No connection from A to D, connection A to alpha 5, and it works exactly as I expect. B to C, no connection. B to D. Oh yeah, just 5. Well, that works. And wow, this is not difficult. B to alpha 3. Okay. You'll notice I've missed out this bit. The reason I've missed out this bit is because all we're asking here is B and A connected, but we've already asked it A and B connected, so it's just going to be the same. So the whole thing just actually reflects across this diagonal, so I don't need to fill this in yet, I can just reflect it at the end. That's how I prefer to do it. You can do it that way if you want. Maybe it'd be better to do it that way. Let's do it that way. It's probably clearer. B and C. Do B and C connect? No, they don't. Okay, does C connect to D? It does, with an edge of 7. Does C connect to alpha? It does, with a weight of 3. Does D connect to A? We've already done this once, a dash. Can reflect this, B and D. Yeah, you know what? Reflecting it is way easier. Does D connect to alpha? It does with 11. Alright, and now we just reflect everything. Let's do that. Boop. That has a 5. It's also 3. Wait, I feel like something's missing here. There's 2 5s. Oh, there are. Oh, and now we have a visual representation of that here. You might be like, okay, why should I care? Good question. The reason you should care is because now we can actually do Prim's algorithm deterministically, which is like, what? But somehow it works, so that's cool. I'm trying to rub out these red lines. It's actually a problem, but that's okay. I'm assuming I can just fill in the rest. Ta-da! There we go. Pretty much nailed it. There we go. Nailed it. Alright, so now what we can do, without ever looking at that thing, we can do Prim's algorithm the exact, well, not the exact same way, but pretty similar. So you start Prim's algorithm like we said before, choosing a node. Before I just chose A, just because. What color do I want? Purple. Go with a smaller stroke. So what you do is you circle your starting node, and then you cross out that row. That's just something you do. Maybe I want that a bit thinner so we can still read stuff. Or actually, there we go. Cross out the row. And then what you do is you look in this, oh, hello. Hello, okay. You look in this column and you find the lowest weight. In this case, that's a 2. And then what you do is you look at which row it's in. Here it's in B, so we circle B. And we cross out this column again. Boop. And you just repeatedly do that. So now we look at anything in A or B, which is lowest. Here it's number 3 in B. We're in alpha, so we circle alpha. And then we cross out. Oh, it's really annoying, I can't read chat. There might not be any chat though. If you're in chat, I'm sorry. It's meant to be a short stream. It's ended up being alright. Because nothing's happened that's caused me to have to stop or anything. What's the lowest now? So we're looking at anything here. Or anything here, because we've got 3 things circled now. Just so happens the 3 in the alpha column is the smallest. That's a C, cross out C. Stroke through. I'm actually making more progress in this episode than I thought. Okay, and now what's left? Either 5, 7 or 11. 5 is the smallest. Wow, that's too thick. And that's it. Okay, so what have we done here? Well, now we've got 2, 3, 5, 3. If we sum those up, 2, 3, 5, 3, we get 13. And as you'll recall from earlier, that is the same value. Wow, that is thick again. Okay, where is it? Boop, we got the same answer, and this is actually the exact same connection. So here we got, actually write out the connections here. We've got connections of AB. Oh wow, that's still too thick. Okay. Got connection of AB, because we've got this number here too. It's in the A and B. It's got a row of A and a column of, no, column of A, a row of B. So we give it AB, which means the connection between A and B. Got length of 2, BD. Weight of 5, B alpha, 3, C alpha. This might seem dull, but it's actually important later when we get to the programming. We understand what's going on here. So this can now be constructed back into the spanning tree. So even though we never had a spanning tree, we just had a collection of numbers that represents the network. We can actually reconstruct everything. So we can go AB, BD, boop, C alpha, and what else? Oh, B alpha. There we go. And this is the same spanning tree we got earlier. So that's pretty interesting. Without ever looking at it, we got all the data we needed to construct a spanning tree, but everything we did here, like none of it we needed a human, it was all computational. So for example, at the start we were just choosing the lowest number of 2 and 5. A computer can tell two numbers and tell you which is lowest. Like given this list, the computer will be able to tell you which one's lower. And not only one list, but it can do it with a whole load of numbers. So for example, there's a point where we had like A and B. There was a point where we had a lot more. And it doesn't matter how many numbers you have. So let's say we give the computer, no, you know what, I can show you I can literally show you this. That's far more, way more interesting than doing that. So if we have, what numbers do we want? I don't want to put them in order though. Okay, so given that list of numbers, here a human can look at this and go, which one's the lowest number? 3. A computer can do that too. So if we do a.sort and then a0, actually tell us the lowest one's 3. So the computer did that all on its own. That's important. It means that everything we did here a computer can do. And if a computer can do something, that means we can automate it. So that is the goal of this video series. Can we make this algorithm be automated in Python is the goal. Which ultimately is connecting up nodes to figure out the cheapest cost is ultimately what we're doing here. So I guess we can go straight into Python. I need to go very soon. But I guess the first question we need to ask, there's a lot of questions that need to be asked really. In terms of development, ultimately we want to be able to give it any list of numbers. That makes sense. That did not make sense. But to start with, let's just create a collection of ones, just because that's probably the best place to start. Start with dataing stuff in. Start with the very basics. We want to input to the computer. We want the computer to construct this array, just as a starting point. So as a human, we can draw it in 2 dimensions. Computers don't really understand 2 dimensions too well, so we have to spell out in 1-dimensional setting. So what we can do to spell it out 1-dimensionally, we can split these up. Do you want rows? There's 2 ways we could do this. We could either split it into 3 arrays of 1s like this, of row arrays, or we could split up into 4 column ones, so we could split into an array like this. I'm going to do it rows for now. I don't know which is better. Maybe it doesn't matter. Let's just do this for now. And I'm going to end the episode. Okay, so how does this look in Python? Good question. I think it looks like this. Does it? Let's call it big, for I in range 3. I'll explain what's going on in a second. Append 1. Should be good. And after we've done that, we've append small. That might be it in terms of code. Let's see if that worked. Oh, I need to save it somewhere. Oh no. Where am I going to save it? What am I going to call it? Let's go desktop. Prim's D1. Alright, let's see if that works. Oh gosh, why is that lagging? There we go, we did it. So as you can see here, we've constructed, in a linear way, we've got 3 lots of 1. So how this works is we've got a for loop of 3, which just means repeat this section of code 3 times. And what it does is it repeats it each time, but it has a different value of I each time. That's why I put for I in range 3. So see here, it's got 0, 1, 2. So what this is doing is basically that. Basically saying, or That'll do the exact same thing. Print out the exact same code. So basically it's saying for a variable name in a list, and we can condense that as range 3. That's the exact same thing as 0, 1, 2. For a value of I of that, we're going to execute this code, but we don't actually need to reference I. It's pretty much just a repeat 3 times code. So what we do is we set up a small array, and then we do a for loop of 4 times. We just add the number 1, append meaning add, just add 1 each time to this, and then eventually we add small to big. So that's how we get 4 rows within our matrix thing. So I guess that's a good starting point. There's going to need to be a lot going on eventually. The big things, I think, eventually, so we need the user to input the numbers, which is going to be fun, probably not too bad. Inputting in Python is not too bad. Like, for example, if we just wanted, let's comment this out. 3 did means comment, it just stops the code from doing its thing. Like, for example, if we did, getting input's really easy in Python. No, you know what, I want this better coded than that. So prompt text is completely arbitrary, it can be whatever we want. I'm going to do that just so it looks nice and so the user can easily see they're meant to type something in. Then you have input, it takes 1 parameter here which tells it how to do it. Here we just got that thing which is going to display to the screen. And then we could do like that. Is that going to run? Why is Python lagging? It's not doing anything. Well, it's doing something, very little. Okay, let's so put apple space, then it will just print out apple 20 times. So as you can see, this thing here just ends up here. Not too complicated. So as you can see, we can get input from the user. Here we've got apple, and then we can use that input, and we can put a different input. So we'll be able to use this idea here to get input later from the user into our matrix thing over here. In fact, we could already start working on that if we really wanted. Let's do that. So, call it array element. Alright, so we're getting an array element, and then step 1 will just have it be the array element, which is the user's input. Oh, and there's an important thing we need to do here. We need to say what type of input we're getting. Here is an int input. Before, we should have specified, but we didn't. The default's string, so it worked, and string is just a word. So before we were just inputting a word. We should have specified here. We should have said string to say it's a word. I didn't, but that's okay, because by default it's string. But yeah. So now we actually have control. Now we've got 77, 77. Obviously we're going to need to make this more advanced so we can say specifically what each element is. But it's a pretty good starting point, pretty good stream one. So that's it really. Alright. So I hope that you learnt something, or not even learnt something. I hope that was somewhat interesting. I guess I'll be continuing with this. Trying to, the end goal is literally to have this thing done with this stuff. You know, that algorithm I did at the start of crossing stuff off. So we'll get there eventually, hopefully. It's kind of difficult, but we'll see.